Hi everyone, my name is Kyle Knapp and I'm a software developer at Amazon Web Services where I primarily focus on developing client-side tooling for AWS. So projects that I work on include the AWS CLI, the AWS SDK for Python, and AWS Chalice, which is a Python serverless microframework for AWS. And today I'm going to talk to you about the best practices, lessons learned, and how-tos from developing Chalice with regards to automating code quality. So, when I talk about automating code quality, I'm not talking about removing the human completely from the code review process, but what I'm referring to is removing the number of manual steps that a human may be doing currently that they don't necessarily need to do, and instead offload those to the machine. As to some examples of ways you can automate code quality checks, you can see some in following standards. So taking this code sample here, you'll see the following issues with it related to standards. So the function name has a camel case. That's a PEP8 violation. PEP8, if you're not familiar with it, is the Python coding standard for style. So make sure you read up on that. And specifically, you want to be using snake case instead of camel case. The second issue is related to PEP257. This is related to docstring style. You want to keep your docstrings to one line if they're one-liners. And finally, there's another PEP8 violation related to having make sure you have white space around each of the assignment operators. So another example that you can automate is following safe practices. So I have a function here. You notice at the very end that there's a default mutable argument value, and that is a dictionary. And this is an issue because when a function gets created, the default argument values get created as well. So if I was to go ahead and call it with foobar, it'll return foobar back, but when I call it again with bizbaz, it'll get the foobar from before because it's using the same dictionary from before when it gets called. Another example of following safe practices that can be checked with code quality automation is making sure you're not accessing internal methods outside of a class. So if it begins with an underscore, that means it's an internal method or attribute. And if you're using it outside the class, there's a chance it can break because the developer may make a change that's backwards incompatible or even remove the method altogether. So all these examples are pretty simple, right? But when you give 100 lines of code, it becomes a lot more difficult to detect these, and a lot of times you may miss some of them. And in the end, it's going to make your development processes a lot safer and more efficient. Furthermore, a lot of open source projects out there automate code quality today, such as Django, Pandas, Twisted. And one open source project that I want to talk about is Chalice. I mentioned it before, but Chalice is a Python serverless microframework for AWS, so it lets you write AWS serverless applications. And the way it works in Chalice for how automated code quality checks work is when a pull request is sent to the Chalice repository, the commits that the contributor provided are run under quality checks run by a machine. And if the checks pass, you'll see a green check mark, and the machine will let you know if all the checks pass, and hence giving it sign-off for this pull request. This allows the reviewer to go in, review it themselves, and also give them sign-off and go ahead and merge. So with this now end state, let's talk about the benefits you get out of this automation. So the first benefit you get is it enforces quality checks. So here's an example of a pull request where someone submitted some code. It didn't pass the quality checks to start. And in fact, none of the other commits also passed as well. And as a result, the machine didn't give a sign-off, and therefore the code cannot be merged because the checks need to be passed in order to be merged into master. The second benefit is it's going to improve your code reviews. So here's another example of a GitHub pull request sent to Chalice, where as a first-time contributor, they provided the commit, but it didn't pass the checks. So they quickly went ahead and tried to fix some of the errors. So looking at this specific one, it was a PEP8 violation. It was longer than 79 characters, so they went ahead and fixed it. There was a couple more issues they had fixed, but eventually they got the builds passing, allowing one of our reviewers to come in and go review it. So there's a few points I want to point out related to how it gets improved. So one, it enables faster iteration cycles. You don't have to wait for a reviewer to come by to get feedback. The machine's giving you feedback for your code. Secondly, the reviewer, it makes it a little bit easier for them. They don't have to worry about looking for as many issues. And the third improvement is that it's going to make a better experience for the contributor, because if there is a lot of feedback, it's a lot less personal when it comes from a machine as opposed to a human. And finally, the third benefit I want to outline is the machine is essentially a safety net. So to pick on me now, here is an example where obviously when I submitted the pull request, I did not run the checks locally, and the build failed. The machine told me that, and I quickly went ahead and fixed the type check issue I had, and it passed. So I like to think I'm pretty familiar with all the checks that we run, but I do make mistakes as well, and it's nice to have that safety net. So let's talk about, now we know where we want to be, let's talk about how we're going to get there by looking over the steps it takes to automate all of this. First, we're going to have to identify the tools that we need for improving the code quality, how we can make it easy to run and easily run in a local environment, and then how do we enforce this across a team or a project. So to dive into some of the tools, the three tools I'm going to cover specifically are Flake 8, Pylon, and Coverage. I recommend using all three of these tools. We use all three of these tools in Chalice today. Starting with Flake 8. Flake 8 is going to analyze your source code and run these three tools underneath of it. So Flake 8 is just a wrapper around these three, specifically PyCodeStyle, PyFlakes, and McCabe. In order to use Flake 8, you can just pip install it, and run it on a single file. It'll tell you all the errors it sees, and also you can run it on a directory to get all the errors for all the files in that directory. Starting on with PyCodeStyle, that's the first tool it wraps. PyCodeStyle is going to be looking for style issues specifically related to pip8 and also non-Pythonic usage. So looking at this code sample, here is a function called print evens, just prints out the even values, and if we run Flake 8 on it, it'll print out these errors related to PyCodeStyle. And looking at one of these errors, it'll tell you the file it happened, the line number, the error code ID, so this identifies what exact error was. There's a category you can determine, and also the description. And if I was to highlight all of these errors, you'll notice that Flake 8 is pointing out the multiple spaces before the in operator, lack of spaces around the assignment operator, and the use of equals equals true, which is not Pythonic. And if I was to go ahead and fix these, it'll create a clean run through of Flake 8. Mainly just I got rid of the equals equals true and fixed up some of the spacing there. Moving on to PyFlakes. It's different than PyCodeStyle because it's not going to be looking at your style. It's going to be looking for code bugs. And it only emits errors for issues that have a low probability of false positives. And to look at some of the errors that PyFlakes may show through Flake 8, let's go ahead and run Flake 8 on this example. And you can see that it's going to notice that there's an unused import, and also at the bottom there is a typo in is divisible, the second usage of it, and that's throwing two other errors related to variable assignment and reference. And in order to fix that, you can go ahead and remove the import statement and also add the I back in divisible and get rid of all those errors. The final tool that Flake 8 encompasses is McCabe. So McCabe is a complexity checker. What it's going to be doing is calculating McCabe complexity, which is the number of independent code paths a piece of code can have. And generally, if the code is complex by McCabe complexity, you're probably going to have a lot of bugs. So we want to make sure we have a low McCabe score. To walk through some examples of how you calculate it, here's the identity function. What it's going to do is just return the argument that was given. There's only one code path, which is just return that value. Is McCabe complexity is 1. You go to its second function, where it's just an if statement. One branch of this if statement returns true. The second one returns false, and therefore there's two code paths and has a McCabe complexity of 2. The final one is contains all. This has an additional if statement, and it calls the contains, which has a McCabe complexity of 2, and thus the additional if statement is going to add one more layer of complexity, making it a McCabe complexity of 3. So now, in order to use McCabe complexity with Flake 8, you have to opt in with the max complexity flag. So by specifying 2, Flake8 will complain that the bottom function is too complex, as its McCabe complexity is 3. As a rule of thumb, it's a good idea to use the value of 10. McCabe did a lot of research to start, and that's what he landed on, and also there is a lot of external research out there to support this. This is the value that we use in Chalice today as well. Now that we covered Flake8, let's talk about Pylint. So Pylint, it's very similar to Flake8. It's going to look for coding standard issues. It's going to look for styling issues, any bugs. But the big difference is it's generally stricter and more opinionated than you're going to get out of Flake8. So you're going to get a lot more errors. It's similar to Flake8, where all you have to do is pip install Pylint. You run it on a single file, or you can run it on a set of files in a directory. Moving on to a code sample of how Pylint looks when you run it. If you run Pylint on this example 4.py, you'll see the following errors out. You notice this is a lot more errors than you would have expected from Flake8, so let's go ahead and dive into it. To start, an error begins with the category, so this is C for coding standard. There's a line number. It gives you a message and also the human readable message ID to identify what the error was. And if I was to highlight all the different issues with this code sample, you'll see the following. You'll see there's missing docstrings. You'll see that there's a camel case for load into. There is the dictionary use for default argument value. There's the use of F, which is considered an invalid variable name. PEP8 issues with the equal sign, and also JSON not being defined. So that's a lot. I'm going to go ahead and fix some of these, but not all of these. Specifically, I imported JSON, switched it to snake case. I also got rid of the default dictionary and fixed up some PEP8 things. But I didn't fix everything. Specifically, I have still docstrings missing. I also am still using the variable F. And the reason why I didn't fix these is because I have an opinion against what the opinion that Pylint has. And that's going to happen occasionally, so you're going to want to be able to configure some of these values. And the way you configure it with Pylint is you generate an RC file. So once you have the RC file, you can go ahead and open it up and go to the different section that you may want. So I'm going to show you now how you can disable a message altogether. I'm disabling the missing docstrings. In general, it's recommended to have docstrings. I'm just showing, for the sake of this presentation, how you go about disabling it. So continuing on, you can also tweak how errors are determined in terms of whitelisting a name. So I'm going to whitelist F, mainly because on our team we use F a lot to represent a file object. And now, if I go ahead and run with Pylint with the RC file flag, it will get rid of those errors. In general, with the Pylint RC, I recommend sticking to what Pylint gives you unless you have a strong opinion against it, especially if you're a new user to Python. I wouldn't meddle with those configurations unless you realize otherwise. So I mentioned before the similarities of Flake8 and Pylint. I wanted to recap all of this and try to show what exactly are the similarities and differences. So in terms of Flake8 and Pylint, they have the similarity in terms of they both have plugins, configurations, and they do a lot of the basic checks such as PEP8, looking for unused imports, variable referencing issues, and non-Python idiomatic statements. And there's quite a big differences in between Pylint and Flake8 in terms of what they do in checks. So Pylint's going to be a lot slower than Flake8, but Pylint's going to be doing a lot more checks. So it's going to be looking for names that are valid, so make sure they're PEP8 compliant. It's going to be looking for dangerous usage patterns, so it'll catch those use of internal methods. It also looks for maximums, so if you have too many methods, too many arguments. It also looks for code similarities, so if you are violating dry, don't repeat yourself. It'll look for that. However, so on the other side, Flake8 doesn't have as many checks as Pylint, but it does have checks that Pylint's not going to catch. So has a little bit stricter whitespace support in terms of finding issues of comments. And also it does McCabe complexity. And in general, it's a reasonable approach to actually run both of these in your development process. Run Flake8 first, it's a lot faster, it'll get some of those initial issues out, and then run Pylint afterwards. And in general, by running both of them, you'll cover more issues with your coding, cover more issues, and also you will not run into too many conflicts between the two tools. All right, so now let's talk about the final tool, coverage. Coverage is going to figure out what lines of code have missing tests. And in order to use it, you can pip install it, but most people are going to be using the plugins. So if you want to use it for Pytest, you just pip install Pytest Cove, and you can run it just within your normal test runners. So this is just a normal Pytest run, the Chalice code base, but now I can run it with the --cove flag and specify a source, and also the cove report to give me how I want to output the report. So printing out here, you'll see that there's more statistics at the end of the test run, where you'll see how many statements got looked at, how many misses there were, and the overall coverage at the end. It'll also tell you what lines were missed. And in general, this is helpful because it'll tell you what lines are missing. It's not going to guarantee you perfect test quality, but it'll help you in achieving great test quality by telling you where your blind spots are. And you can also improve on top of this by looking at branch coverage. So branch coverage is the idea that you're going to make sure you hit both sides of a branch in a test. And it's important because you can still have 100% coverage, but still not have 100% branch coverage. And it's really easy to enable. In a coverage RC file, you just have to specify branch equals true. And if you run PyCove again, or Pytest again, with coverage, you'll get the following. So you'll see there is a branch. This tells you how many branches you went over, and also there's a branch part saying how many branches you missed. And also notice that the coverage went down from 97% to 96% because we are missing some branches. Finally, if you want to visualize this, you can use the HTML report option. So that will generate an indexed HTML that you can open, and it'll tell you exactly what lines are missing, even tell you the reasons for why you're missing a specific branch. So now that we covered coverage, let's go ahead and talk and recap the tools that I covered. So when I'm thinking about the tools, I like to think of this diagram where I have 4 different buckets of things I'm trying to check in terms of code quality. There's style, which includes standards, if it's Pythonic. There's bugs. There's documentation in terms of style. And then there's usability, a little bit more gray area when it comes to how you name your abstractions, your classes, your methods, how many arguments, and how many methods you have attached to it. So as it relates to Flake 8, Flake 8 is going to be covering your style with regards to PEP8 and then your bugs. Pylint, on the other hand, it's similar to Flake 8, but it does a little bit more, has more checks. It's going to be looking at documentation specifically to make sure you at least have docstrings, and also usability with regards to making sure that your names are correct and also that you don't have too many arguments or methods to an abstraction or interface. Coverage, it's going to catch it's going to tell you what lines of code have missing tests, and you can add tests that way. So those are the 3 tools I covered. There's a lot more tools out there. There's also a lot more tools that we use in Chalice in our code quality automation checks that I wanted to do a quick shout out to before moving on. So the first one I was going to mention is MyPy. MyPy is a static type analysis tool. It's awesome because it's going to catch a whole set of bugs that Flake 8 and Pylint aren't going to catch. Specifically, they're going to be catching the ones where you're making the incorrect assumptions on what the type's going to be. There's PyDocstyle. It's going to enforce PEP 257 standards for your code base, and also Doc8, which also enforces correct usage of restructured text and Sphinx styles. The thing is, there's many more tools out there. I recommend doing research, identifying places where you're doing checks today that are done manually but could be automated, in which case find a tool that appropriately fits your need, or even write your own. So now we have all these tools and all these configurations. How do we make it easy to run all these? The way we do it in Chalice is in the repository, you'll have 2 files. There's requirements-dev.txt and a make file. These are the main 2 files we need to get up and running with the process. The requirements-dev.txt is the requirements outside the runtime requirements of Chalice, where I can specify all the different tools that I'm going to need. So I can specify coverage. You'll notice there's Flake 8, there's Pylint, and also we lock to specific versions. The reason why we lock to specific versions in requirements.dev.txt because it ensures that we don't automatically upgrade our tools, because if we do, there's a chance we pull in a new check, pull in a new bug that might break our builds and force us to immediately upgrade. By locking, we can upgrade on our own watch. In order to install it, it's very simple, pip install -r. So now we have all the tools installed, let's talk about the make file. The make file is a way for us to organize ways in order to be able to easily run all these checks. And the way we've broken it up is for each type of check we want, we have a separate rule. So we have the check rule that does all the flake8, it does PyDocstyle as well. There's PyLint rule and a type check rule. And it's very easy to run. You just run make check, and it will go ahead and run flake8 on the Chalice source code. I can run on a specific file if I had a specific configuration I want. Also, I can run it on the tests to make sure those are up to snuff. There's also PyLint. If I do the same thing, I'll run on Chalice source code and also run it on tests. We even have our own custom plugin for PyLint to do additional checks for our tests. Continuing on to the second page of this, note that this is on a second slide, but it's the same make file. We have rules for tests, docked rules, and also at the very bottom you notice there's this PR check. So this PR check's interesting because we see it as running the gauntlet of checks. So if I was to run make PR check, it would run the check rule, the PyLint rule, the coverage rule, the doc check rule, and the type check rule. That's a lot. So if we get through all those recipes, we feel that the code would be in a very good spot to send up for a pull request and up for review, and eventually merge into master. And if we want to set this standard that we run make PR check, let's talk about how we can go ahead and automate it for a team setting. In the end, it's going to be very easy. All you have to do is enable it with the CI system. For us, we use Travis. So what Travis is going to do is we have the following build jobs. We have a Python 3.6, Python 2.7, and then from there, we'll just run the make file. And specifically, the rule we're going to run is the PR check and the PR check py2 for 2.7. And then from there, whenever someone submits a pull request, they will have a Travis build submitted to them. Notice that the PR check job is running and a PR check py2. And if those builds pass, Travis will go ahead and give the check off for that pull request. So there's one more check that we have for the team setting, and it's related to coverage. So at the very end of the Travis jobs, we'll go ahead and pip install CodeCov and run the CodeCov CLI. This will take the coverage reports generated from the Travis build and upload it to a coverage service called CodeCov. And the nice part about CodeCov is it will go ahead and add an additional check to make sure you're not losing coverage on the pull request you're about to submit, and also will comment and tell you about what areas, tell you the diffs for all the different changes you're making. So it gives you a nice visualization that way. So with those two checks in place, let's revisit another pull request, the same pull request I sent from before, where I had failed the build. Opening up that red X, you'll notice that there is it was a Travis build that failed, but the CodeCov one's passed. So that's the Travis one, CodeCov. And then with that, I noticed that the Travis build passed because the type checks failed, and as a result, I updated, and all three of the checks passed, which means that I'm in a good spot to go ahead and get it reviewed and get it merged into the master branch. And to recap the benefits of automated quality checks, let me go over them real quick to refresh your memory. So first, it's going to be a lot faster and more accurate for a machine to do it than a human. So take an example of the previous pull request I just showed you. The machine caught something that I didn't. Adding new code quality checks is easy. So if there's a new check you want, all you have to do is run it on your source code, make sure it passes, and then add it to your make file, and it'll automatically be ran by your CI system. It sets a standard that code quality checks must pass in order to get merged. The machine doesn't waver. It's just a strict white or black. It has to pass. And finally, it's going to improve your code review cycles. So it's going to get you a quicker iteration in terms of feedback for the contributor, and also for the reviewer, it's going to make their job easier because there's less things they're going to have to worry about. So once you have all this automation set up, it's not something that you just set up once and just forget about it. It's something you set up and make occasional updates when needed in order to make sure that your automated code quality checks stay healthy. So there's a few best practices that I would recommend based off this. So the first best practice is always be improving quality checks. If you see something that could be checked that is currently being checked as manually, try to automate it. So a good example of this is here, where when Chalice moved from the AWS Labs organization to the AWS organization, we forgot to change some of the links from AWS Labs to become AWS. So we could have just fixed the links and been on our merry way, but instead we fixed the links and added a check for it. So if you highlight right here, we added a docstring check. So the benefit of that is that it ensures that there's no other broken links, and also there won't be any future broken links in Chalice. So that was a good example. On the flip side, you want to be avoiding compromising existing checks. So you don't want to be loosening the restrictions or disabling a check completely. As an example, here is a commit where in order to get the checks passing, you notice that the git commit message said get test passing. They decided to take the max complexity from 10 and put it to 11. Generally, you don't want to be doing that. You have these code quality checks there for a reason, specifically to make sure your code quality is up to snuff. And you want to be fixing the code, not the test, when you're making these changes. And honestly, if you're at a max complexity of 10, we probably should have done some refactoring to get it a little bit lower already. All right, so third best practice. This is a tricky one. But specifically, it is you don't want to fall under a false sense of security with these automated code quality checks. You still want to be doing thorough code reviews of what you're submitting. So here's an example of a PR that I sent. It was a quick bug fix. It was about a 2-line change related to making sure that defaults get reverted back to. The extra code I added here was mainly tests. That was a big part of it. And it also passed the checks. And in the end, I ended up closing it, mainly because if you look at the subsequent pull request I sent, I have a description here. So when I originally sent the pull request, I blindly just made the updates to pass the test I wrote. I was like, okay, we're all good. But when I looked at it again, I realized I don't think this is the right approach on how we should be doing this. I'm adding default specific logic to a general purpose function. So instead, I refactored it to add it into the configuration logic. And it ended up being a lot better in the end. It made it a lot easier for us to test. So you always got to be doing thorough code reviews in the end. So now that I talked about how you can upkeep the system, let's recap what I covered in order to build the system. First, I talked about the code quality tooling. So I talked about how you can use Flake 8 to catch PEP8 issues, also code bugs and complexity issues. Pylint, similar to Flake 8, it's a lot more stricter, has more checks, and will be more opinionated. Talked about coverage and how you can use that to determine where you're missing tests in terms of lines of code. And there's many more out there. Like I said before, ideally you should be doing research to see what tools you can use, what checks you're doing currently that are manual that could be automated, and find the appropriate tooling, or even write your own. You can even write scripts, plugins for Flake 8, Pylint. There's a lot of options out there. Once you determine your tooling, you need to be able to manage it. So the way we do in Chalice is recurrence-dev.txt to isolate what tools you want to install. And then we use the make file to make it really easy to run these tools. And finally, once you have the local environment set up, you need to automate it to make sure everyone else is following by the rules and checks. And to do so, you can use CI systems to run these checks. You can use coverage services to make sure your coverage is upkept, and also make sure you're following the best practices once this is all set up. And with that recap, here are a couple links that I wanted to share for you all to go ahead and look at after this talk. The first link is to the Python Code Quality Authority. This has a lot of cool tools out there that can help improve your code quality. The second one is to the Chalice Repository. The purpose of this link is so you can dive into the source code yourself to see how Chalice does it. And with those links, I want to thank you all for coming and listening to my talk. I really hope you got a lot out of it. Thank you.
All right, so if there are any questions, I invite you to talk to Kyle offline. Use his contact info. Let's give him one more round of applause.